Over to the cloud. All right, we're all set. Okay, what did we do last time? That's a good question. What did we do last time? I got started on, actually I continued our discussion of Lyapunov's second method. Remember, that's an alternative way of analyzing stability of fixed points. And there were reasons for developing an alternative way. Our main tool has been linearization. And generally speaking, that is I would say that's the best first thing to try. Except there are two major limitations of linearization. One of them is that when you, especially in conservative mechanical systems, and I'm just trying to scroll to the point where I was making these, you can have non-hyperbolic fixed points and whereby linearization is inconclusive, therefore you don't know what the non-stability properties of the fixed point relative to the full system are, but you want to know. So you don't just want to give up. Then it would be nice to have an alternative that gives you a tool that doesn't just get stuck when the linearization reveals a non-hyperbolic fixed point, but it still gives you some idea about the nonlinear behavior. So that's reason number one. Reason number two is that linearization in some sense, although it gives the right answer when the fixed point is hyperbolic, namely, especially in the most important case when the fixed point is stable, asymptotically stable, it gives the right answer, but it may be misleading in the sense that a attracting fixed point, an asymptotically stable fixed point that you might establish, whose existence you might establish from linearization, might actually have a tiny domain of attraction. So the linearized stability analysis tells you nothing about that. So you feel comfortable, and yet in real life, you in fact perceive that potentially that equilibrium point to be unstable because its domain of attraction is tiny. And I gave you this sort of classic example, which the fluid mechanics community is still scratching their head about, is the problem of transition to turbulence from a base flow, which is fundamentally stable under linear approximation. And that appears to be correct. The Navier-Stokes equation correctly predicts that, but its domain of stability for the base flow is tiny, and it's shrinking as the Reynolds number goes to infinity. So in practice, you're not able to keep a flow laminar at very high speeds, even though theoretically it should stay that way, simply because any tiny perturbation then gets you out of that tiny shrinking domain of attraction. So anyway, so that's kind of a high profile example, but there are other areas in applied science where that example is highly relevant. So we went through the main theorems of Lyapunov, which basically all rely on the assumption that somebody gives you a function with good properties. Just review the first such theorem, that if you have a scalar valued function, which is say once continuously differentiable, defined on some neighborhood of this fixed point, and the function is cup-shaped, so or positive definite, as we say in more mathematical terms, meaning that it vanishes at the fixed point and it's larger than zero away from the fixed point, at least in that vicinity of the origin. Then in addition, if in addition to that, its derivative along trajectories, which is given by this inner product, is negative semi-definite, then you can guarantee asymptotic stability for the system in a nonlinear sense. Okay. And it may actually happen that your linearization would actually be inconclusive. And yet, when you have such a Lyapunov function, then you don't have to give up on the linearization, which might give you, a zero eigenvalue or something. If the Lyapunov function satisfies all these properties, I think I didn't emphasize this, but this can actually be a stronger result than in the same problem as relative to linearization. And also the additional statement, which I just added, it's not hard to see, it's not part of Lyapunov's classic statement, but this is what brings you closer to understanding the domain of attraction, is that if you can guarantee that on the closure of the domain that you're considering, if you remove x naught from it, you can guarantee that the Lyapunov function has non-vanishing gradients away from here, And then the largest level set of V, let's call it W, which is fully contained in U, and I'm showing that here, that's actually a lower estimate for the boundary of the domain of stability. So if you start inside that set, then you're guaranteed to be in the domain of stability, meaning that you're not going to see growing oscillations from there. And I went through the proof and I just added this in the end, this additional kind of remark. You can strengthen the claim of stability to asymptotic stability if you require slightly more, that you actually require the Lyapunov function to be strictly negative definite as opposed to just semi-definite. The geometry of it is here, that these are the level surfaces of the Lyapunov function, and this condition then guarantees that you're crossing them strictly inwards, okay? And likewise, that same idea then can be carried over and prove instability, namely if you have a positive definite Vx and hence its neighboring level surfaces are spherical, okay? But you have this V dot, which is given by this inner product, is strictly positive, then the geometry says that the trajectories are crossing these level sets outwards, and then you can guess the statement of the theorem that the equilibrium is unstable. There's another frequent situation in which you can prove instability using theorem 4, which is the case when you find the Lyapunov function, as we call these functions in general, which vanishes at 0, but instead of being of cup shape, it is like a saddle surface, so it's indefinite, meaning that arbitrarily close to the equilibrium point where it happens to be 0, the function has negative values as well as positive values. So if it's a smooth function, then generically this is its shape nearby. And then you require V dot to be definite. Interestingly, it doesn't matter whether it's positive or negative definite. Either way, you are able to conclude instability. And my cartoon proof shows the reason why, because you kind of have this V shape defined by the 0 level sets of this hyperbolic type profile, right? And if V dot is definite, then you're either moving in this direction from the surface positive definite, then you're moving from negative values of V to positive values of V, or if it's negative definite, you're moving the other way around. But that motion ultimately gets you away from the vicinity of the equilibrium point. You might be, say, going in this direction because I think this was this is the negative level set, and V dot assume is positive definite. Then for a while you're doing well, because you're actually, for all we know, you're getting closer to the origin because the increasing level sets are closer and closer to the origin. But then nothing stops you from crossing this 0 level set, and then what has worked to your advantage now is working against you, because you have to keep crossing increasing level surfaces, and the only way you can do that is just by moving away from the origin. And the same happens when V dot is negative definite, right? So there's something to keep in mind. And I started looking at the pendulum example, which is really an incredible source of examples for everything. Of course, in the problem sessions, you look at more complicated examples. But the pendulum is just, I think, perfect for illustrating a lot of the phenomena without getting lost in the computational detail, right? So here was the pendulum, and here was the physical equation of motion with m mass, L is the length, phi is the angle, G is the constant of gravity, and the energy of the pendulum. So I wrote this out. Often I write it without, I write it in dimensionless units, but here I wrote it out in the real dimensional units. Phi has the dimension of a radian, because I want it to be accurate when I write out physically the total energy of the system, the total mechanical energy, which is the kinetic energy plus the potential energy, is the kinetic energy, potential energy, because that's always a good first bet, since it's a scalar valued function, the energy, and it has a lot of the physics in it, right? So it knows the Lyapunov function somehow has to be connected to your system, right? It somehow knows the in and outs of your system, and the first natural candidate for that is always the energy, right? So one has to work in the phase space though. So I introduced x1 is phi, x2 is phi dot. So I rewrote the system in the phase space, at which point this is the right-hand side. I kept these are still dimensional variables, though, so I kept the dimensional energy, and I tried my luck on the energy as a potential Lyapunov function, and we went through that. So at this fixed point here, the energy is 0 at 0, so don't have to modify it. I could just add a constant or subtract if that wasn't the case. So this is always enforceable. What's not enforceable by adding a constant is that the gradient of the energy has to be 0 at that point, because that has to be an extremum. That's what makes the function, cup-shaped. That's okay here, that checks out. And the other condition for that function to be cup-shaped, a potential Lyapunov function, is we need to check the Hessian. We wrote out the Hessian in general, which is this matrix, and it's ML squared, so it's positive definite. Actually, it's not in general, but because this number is in general, because when I take second derivatives, then I will get a constant no matter where I am. But elsewhere, I'm differentiating this quantity here, which keeps changing. It never loses x when it just keeps switching between sine and cosine. So I've already plugged in the particular location. So let me just say that I'm taking this at 0, 0, right? And that's when it's ML squared. This is positive definite. E is also positive semi-definite on u r squared near x naught equals 0. E is positive definite. Sorry, I'm not there yet. So that was the conclusion, okay? But then we had to check the derivative of the energy. The derivative is expected to be 0 because it's conserved on this conservative system. I just checked it out. But when you calculate the variation of the energy along trajectories, that's exactly the same as checking that condition on the Lyapunov function. That's where it's coming from. So in the more general setting, when the Lyapunov function is not the energy, you're checking the conservation of the Lyapunov function along trajectories, okay? And what you should be getting, that it's at least not growing. Here, more is true. It's constant. We knew that going into this. I just went through to make sure that I didn't make any typos. So E dot is negative semi-definite, because being 0 is a subcase of being negative semi-definite. And that's true on the whole phase space. So then by the first theorem that I quoted from Lyapunov, x equals 0 is Lyapunov stable. And mind you that under linearization, and this is Lyapunov stable period, not for the linearization, for the whole system. And if I had used linearization, I could not be making this conclusion, because the real parts near a center are 0. So strictly speaking, linearization, throws his hands in the air, or her hands in the air, depending on your view of linearization. And then you say, I don't know. This is not an asymptotically stable fixed point. I can't tell you for sure what's happening in the nonlinear system. The Lyapunov's second method doesn't care about that, and immediately gives you a statement about the nonlinear system, which is really great. I also went and checked this second statement here, just how that works out in this context. What was the second statement? That if you find that on the closure of the domain that you're working on minus the equilibrium point, the gradient of V is non-zero, then the largest level set of V is a good estimate for the domain of attraction. It's a strict lower estimate. It can be potentially larger, who knows, but it's at least this big. And I told you that if you were to just blindly, of course, on the pendulum, we know exactly what's going on, but that's why I'm using it as an example. But if you didn't know, because it's an example you're in higher dimensions, you're trying to explore, you can certainly plot the level surfaces of a function without knowing it's a scalar fact function. You don't have to know the dynamics. And then you would come to the conclusion in this case that, well, if I take U to be this large, then things are satisfied on it, so I could make the statement that within, using this Lyapunov function, this equilibrium point is stable, but I would not have a good domain of stability estimate from this, because on this domain that I'm showing currently, I have 2 points where the gradient of V vanishes, so I cannot quote that add-on. However, if I shrink it down to anything smaller than that, and this can be arbitrarily close to the separatrices, this choice, then why don't I actually pick it to be one of the level sets of bounded by one of the level sets of V? Then according to that theorem add-on that I gave you, this is an estimate for the domain of stability. And indeed, when I say estimate, it doesn't mean that it's sort of an approximation. No, it's a rigorous in the sense that it's at least this big, right? And you see that for any finite choice of that level curve, indeed, the domain of attraction is at least this big, right? And you could continually refine it, getting arbitrarily close to the separatrix, but you cannot technically pick the separatrix in my statement because that contains this point where the gradient is 0. Any questions?
Yes, may I have a quick question?
Let me just increase the volume, Ahmed, because I couldn't hear you. Please go ahead.
Yes, could it be that there is one choice of Lyapunov function such that one theorem applies and another choice of Lyapunov function such that another theorem applies? What got me thinking about this question is that for a problem in the assignment, in the problem set, there is this problem where the mechanical energy will not work, and so instead we're multiplying by alpha dot and then integrating in time. So could it be that different choices of Lyapunov functions say different things, apply to different theorems?
I think it can happen, but those two statements cannot contradict each other. So you may have a choice of a Lyapunov function that guarantees stability, and another choice of a Lyapunov function guarantees asymptotic stability. These are two different statements, but they do not contradict each other, right? Because if something is stable, then it can also be asymptotically stable. Who knows? Maybe I have a more refined choice of a Lyapunov function, then I get it. If something is asymptotically stable, then surely it is by implication stable. So if the two choices of the Lyapunov functions contradict each other, then there's something wrong with the calculations. Then conditions are not satisfied.
Okay, thanks.
In other words, you're welcome. So in other words, you cannot get from one of them that the equilibrium is stable and from the other one that it's unstable, right? Okay, anything else? All right, let's move on. Before I move on, actually, I wanted to make a note here, is that in a physical situation, the pendulum would be damped. So note, there's always some damping, and if we add, and the poor man's choice is always adding linear damping, which usually qualitatively works, although it's debatable whether viscous damping is really applicable here, but at least that's the first order modeling. And very often this is what people do when it gets satisfactory results. So if we add linear damping to the pendulum, then that changes the equations of motion. So the equations of motion then become ml squared, which doesn't change. That's the moment of inertia phi double dot. But then you get this c times phi dot, where c is the coefficient of damping, plus mg l times sine phi equals 0. Okay. How do I get these terms? For those of you who don't work with this every day, then the damping force, here, this is the angular version of F equals ma. This would be the ma, except that instead of m, you have moment of inertia. Instead of linear acceleration, you have angular acceleration. And that should be equal to all the forces on the other side. And this is the torque exerted by gravity in the negative direction. And this is minus c times cf dot, in that case, on the other side, which is a dissipative force, which opposes the direction of the motion. That's why it's minus phi dot. And you have some constant there, a damping coefficient. So that's how it comes in when you derive the equations of motion. Now, in that case, and this is more, reasonable physically. Now, the energy, what's the energy now? And I'm just bringing this up because I taught undergraduate dynamics a few times, and in cases like this, people suspected that the addition of damping changes the energy. but the energy doesn't change. Damping is a mechanism that will dissipate that energy. But when you compute the energy at any point in time, you still use the kinetic and the potential energy, except that it will not be constant anymore, because if you compute it at some other time, it will be different. And that difference is due to damping. But the definition of total mechanical energy hasn't changed just because I added damping. It's still the kinetic energy plus the potential energy, right? So, so that will be same as before. So if it's the same as before, then the statement about the shape of the energy is unchanged. So E as a Lyapunov function is positive definite in a neighborhood of 0, 0, which is, x1, x2 equals 0, 0, right? That hasn't changed. What will change when you add damping is the derivative of that Lyapunov function candidate, because it will no longer be preserved, that function. So when you calculate E dot, I leave that to you, but again, you would, what you do is dE, now in physical coordinates, d phi dot plus dE, the partial with respect to phi double dot. And when you plug in, then instead of getting 0, when you plug in the equation, now you get minus c times phi dot squared. So that's probably believable, right? So it's negative. It has a negative sign. And the direction of phi dot doesn't really impact the dissipation of the energy, because if the pendulum is swinging in this direction, the damping is acting, so it's taking away your energy. Or if it's swinging in that direction, it's acting the same, it doesn't care. It's the same mechanism that dissipates. So the energy dissipation rate should not depend on the sign of phi dot, but rather on the magnitude of phi dot, and that's exactly what you get from here. So this is believable. In terms of the coordinates that I use in the phase space, this is minus c times x2 dot squared, right? So the question is that, can I now, with this addition of physics, which is certainly a whole lot more realistic than what I just had a minute ago, can I now go ahead and conclude what I really know to be true, which is that the equilibrium point is in fact asymptotically stable because the oscillations will go down to 0, right? So I know it's 0. They're not gonna increase, but ultimately they die out. Do I have a Lyapunov theorem that enables me to conclude that? Anybody? And that's a good excuse for a coffee on my end.
Yes. Theorem 2 states that...
be careful, it's a tricky question.
Okay, yeah, I don't think, okay.
but that's exactly what I was hoping for, because that's what I would say if somebody presented this for the first time. Don't feel bad about it. You are the victim. Thank you. That's exactly what I would say. No question. Okay. But now that I've given away that, well, actually, I didn't say that this is not right. I just said, be careful. The absolutely most logical suggestion is just what Ahmed made, is that you look at the theorems and say, well, clearly I don't want to apply any instability result because that would be plain wrong. I know what the end result is. Do I have something here that guarantees asymptotic stability? And theorem 2, well, that looks indeed. So I can get asymptotic stability, and at what cost? Well, it's the same assumptions on the shape of the Lyapunov function as in the first theorem. Good, that's satisfied. And the second assumption is that V dot has to be negative definite. So for any xu, but of course, what's really relevant here is that, I mean, I made a mistake there, right? So I need to subtract the origin, because at the origin, since I'm not going anywhere, there's no way that the Lyapunov function should be changing in an autonomous system, right? So I forgot to add that there, but hopefully, see, in all the other ones, I I did add that. So anyway, this is just a minor correction. I'm glad we're talking about this. So that was incorrect as stated, because that would never hold. Okay, that condition, this condition would never hold without this there, because at x naught it's a fixed point, right? By assumption, I have assumed that. So that's a complete trajectory, and since it's corresponding to that, there's a single value of v, which is 0. Then if I plug in that trajectory, I cannot get v dot to be strictly less than 0. At the origin, I will always get v equals 0. So this is not about that. It's about removing the semi-definiteness of v dot in regions away from x naught, still in U. All right. So is this true in our case? Well, and the quick assessment is that, I mean, sure, right? I mean, or is it not? So the question I have to ask, that is it true that this is strictly less than 0 whenever I'm not at the fixed point? Is that true?
No, it's not true.
Not true. Thank you. And why is it? Why is it not?
It's not true at those points where the pendulum stops and reverses direction. So where phi dot is 0.
Where phi dot is 0. So this is phrased in terms of phi dot, right? And you're absolutely right, where phi dot is 0, but what you need to add is that x1 is not 0 at those points, right?
Yes,
so,
yes,
so
right,
that's what you meant, right? So we're exactly. So this is a pitfall that we all. I certainly thank you for the comment, and thank you for everybody for helping to raise the issue. And I only know this because I felt for it the same way when I heard it for the first time. So it's absolutely natural. But the reason I brought this up is we need to really then kind of digest what positive definite and semi-definite, what the difference is. Okay, this function is not negative definite; it's negative semi-definite because it vanishes on a whole line. Okay. And that whole line is x2 equals 0, which is not a point in the x1, x2 phase space, but it's a line. Okay, so basically take x2 equals 0 and any displacement right at the peak of the swing with x1, and this you will get that 0. But unfortunately, it doesn't mean that the function is definite. So let's just write this out. So, but E dot equals 0 on this whole set, which is x1, x2, taken just for simplicity. I pretend that these are linear variables because for my purposes it's okay to say that rather than angular, where x2 is equal to 0. Okay. And that is not the same as 0, the 0 vector. Okay, so it means that E dot is not definite. On U minus 0. And as a result of that, much to my annoyance, asymptotic stability cannot be concluded. And C, this is a case in which then linearization beats the Lyapunov approach. Because had I linearized, I would have the negative eigenvalues immediately hyperbolic fixed point. What I see in the linearization is what I get from my system. So they're able to beat each other mutually. That's the interesting thing. So whichever is more convenient to use, more practical to use, that you use that one. Okay. Luckily, however, people realize this limitation, and there's an extension of Lyapunov's original result, and it's due to Krasovsky from the Russian school, that too. I don't know about the spelling. Probably this would be the contemporary spelling with a Y. Okay, so it's Krasovsky. And if we have that V is positive definite on U minus, let's just say 0, okay, because I'm stating it in the context of this example. V dot is negative semi-definite. So we are in this setting that we're looking at now. So this would be enough for stability. Okay, but I don't want to stop there, because I say maybe I can still get a bit more out of this. By the, I mean, sorry for the clash in my notation. This is now about the Lyapunov function, whereas the potential energy also in most of mechanics is V, at least in analytic mechanics, but sometimes in physics in U. So I'll just change that to U. So that is U, potential energy. So V is then the Lyapunov function, U is the potential energy. So this is not about the potential here, but it's about the Lyapunov function. And then there's an additional condition. So if you look at that critical set, which is, I'm going to write it out. So this is the set of x's in U minus the origin. So I'm not including the origin in that, but I'm asking what is the set on which this derivative is 0. So this is the problematic set, right? This is what keeps me from concluding asymptotic stability. But I have removed the obvious member of this set 0 because that never counts. It's just the rest. So if this contains no full trajectories, of the system, in other words, you cannot kind of survive just hanging out in that set. You may intersect it, but you cannot just travel within that set, okay? You cannot hide in that set and kind of stick it out, right? But you might momentarily intersect, but you have to leave it. So if it contains no full trajectory of the system, then you can conclude, in fact, asymptotic stability. So then x equals 0 is asymptotically stable. And it's a very useful extension. So how would you check that in practice? Well, in this case, you would, so check that here. I need the equations. X1 dot equals x2. X2 dot equals, what was it, minus G over L sine x1. And now I have a damping term, which is an x2 type term. So I have minus x2, and I had a c multiplying it, but when I was, you know, dividing everything, dividing out the leading order term by the moment of inertia, then that had no cancellation of mass with that term, so it fully appears here. Okay, so that's x2. The reason I'm checking it for this example is because you might notice that, wait a second, if I know that much about the trajectories of the system, whether they are contained in a set for all times or not, then I know that it's unrealistic. Then I know everything about the system, right? So why am I even bothering to do stability analysis? It's a nonlinear system. How would I know its trajectories? And you're right, but in fact, that's not too hard to decide whether a trajectory is remaining in an invariant set defined by an equation, by the 0 of a scalar function. So luckily, that is not that complicated. So how would we go about that? So if I call this set something, let's call it Z, because this is the 0 set, the problematic set, okay? So in this case, Z is the set, as we have concluded precisely from here, is the set x2 equals 0, right? Which is basically x1, x2 in R2 such that x2 is equal to 0 and x1 is non-zero, because if I set x1 equal to 0, if I allow for that, then I'm also allowing for the equilibrium point, right? But I don't want to allow for that. Okay. So let's check if that set has the potential to contain complete trajectories of the system. What it would mean in this case, in fact, is that Z is invariant. If I start on it, you stay on it. If I start it, I stay on it, all right? Now, in general, that's not the full invariance of Z and one trajectory staying in Z are not equivalent, all right? Because a set is invariant. If I pick any point on the set, I start a trajectory and I stay in the trajectory. That is not what we're talking about here in the Krasovsky modification. What we're talking about is excluding even just one trajectory staying on Z. So other trajectories might, in fact, for all Krasovsky knows, might leave, but at least one trajectory, if he stays, that's a violation, right? So we should exclude that it should contain no full trajectory. So how do I go after that? Well, suppose that there's this set Z, whatever that is in this case, although I can actually just say what that set is, right? I mean, in this picture, x2 equals 0 is right here. Okay, you could graphically answer this question immediately, whether away from the equilibrium point in U, does it contain full trajectories, right? So I'm here in U, so this is basically the set Z. Does it contain full trajectories away from the equilibrium? It certainly contains the equilibrium, but that's not the question. I excluded that. All other trajectories, however, they hit Z, okay, this is Z, but they go right through it, all of them. So even though the point is that when they hit Z instantaneously, they are in fact tangent to the level curve of the energy, because instantaneously you're not losing any energy. So if you're coming from the outside, from a larger energy level, instantaneously you're tangent, but next time you're inside. And again, when you come here, instantaneously you're tangent, but next time, coming to one of these, I'm not doing a good job explaining, but this is what happens ultimately. Instantaneously, there's no loss of energy at these points, but that's only instantaneous. Next time you're losing energy, you're out. So it's only at discrete points, okay? But in general, if I didn't know the phase portrait of the pendulum and I didn't know the answer, I would just say, well, this is some sort of set, generally speaking. And if I start on it at some point, say here, okay? So if this is my x1, x2, and x2 is equal to 0, okay? Then can I just stick it out and stay in this set? So if x2 is instantaneously 0, then I'm here. Okay. Note, however, that x1 is non-zero. This is how I define my set. So if x1 is non-zero and I'm close to the origin, so I'm not far away so that I hit the other equilibrium point, then this is also non-zero. Okay. Because the only way it could be 0 is that I'm actually reaching the other equilibrium point, but my U is not that big. It's not reaching to the other upper equilibrium point. So this is non-zero. This is 0. So what does that tell you? It tells you that all in all, x2 is changing. x2 dot is non-zero. And since the whole set is defined by x2 being equal to 0, even though you're instantaneously in it, the next second you're out, because it will change, okay? So this is how you would generally check this condition. You look at the defining equation of that set, take a point, plug it into the equation, and see whether the derivatives of the trajectory right at that point take you out of that set, or are they tangent, the derivative of the trajectory to that set? And that's enough. If you're lucky, then they take you out of the set. And in fact, that's very likely. And if that's always the case at each point away from the origin, then you're done. And the Krasovsky modification then tells you the result. Okay, so let me just write this out. If x1, x2 is in Z, and mind you, that means that x1 is non-zero, then x2 dot is non-zero. And you don't even have to check what x1 dot does, because in fact, x1 dot is 0, but it doesn't matter the defining property of the set is x2 being 0, okay? And since that it will be immediately violated, given that you're getting out, no trajectory can stay in Z. And then from that, you conclude asymptotic stability. And I'm just giving you the flavor of this, that just in case you need it, that there's been a lot of work on Lyapunov's original theorems, a lot of refinements. Much of that is actually inspired by problems in control theory, where having a Lyapunov function is really a blessing, because then you can also get some idea about your domain of stability and asymptotic stability. So people were forced to look for alternatives. There are whole books on that. That not recent books, because this is kind of not that I know of. I think that it's a pretty well settled subject. There can be individual contributions, but that also means there's a huge sort of library of Lyapunov functions for whole classes of systems, or for classes of control systems. So you can just do, if you need one, then you can start searching, or even modify the existing ones to your own needs. So that's so much about this equilibrium point, but that's not the only equilibrium point. I spent a lot of time on this particular equilibrium point to kind of showcase what we have. But there's another equilibrium point I just want to see at the, so this is, let me number this. So this was 1. This is, or A, okay? And then I'm going to the other one, which is the saddle point. So the fixed point at x1, x2 equals pi 0. All right, so that's the upright equilibrium position of the pendulum. What do I have there? So the energy seems to be working quite well as a Lyapunov function candidate. So if I evaluate the energy at that point, E at pi 0, is the same expression for the energy, then I get 2 mgl. How do I know that? Because it will be the potential energy up there, and the kinetic energy is 0. So if I go to this expression of the energy, and again, so here, oh, that was a good V. I don't want to change that. So this was the potential energy here, say U of x1, okay? So at the upper equilibrium position, cosine x1 is -1. So when I calculate the potential energy there, this gives me a 2. So I get 2 mgl, and the kinetic energy is 0 there, right? So that's how I got the value of the energy there. Now, this is the classic case of me formally failing the very first condition that the Lyapunov function is 0 at the point of interest. But as we discussed, that's no problem, because I can always just add a constant to this. What do I need to add to this to rectify that situation? I add -2 mgl, right? And that's done, because all the other conditions are independent of that. And you might ask, okay, then what's the point of requiring it to be 0? It makes the statement of the theorem simpler, because then I will not require that. Then I will not say that all the values in a vicinity of the Lyapunov function are larger than its value at 0, right? But I would just say the Lyapunov function is positive definite. That's it, right? So that's the only reason. The simplified expression. So this is not a problem. Subtract 2 mgl. So redefine the Lyapunov function V to be E tilde, which is 2 mg, which is, E minus 2 mgl. And with that, I have really not changed the fact that what I have not changed, well, is that it's conserved without damping, okay? But now my point of interest is no longer the 0, 0. So I need to check, however, what the shape of the function is, okay? Because I'm not at this point anymore where I have made my conclusion about the shape. So the next thing I check is whether the gradient of, because for all Lyapunov functions, it has to be a stationary point, either a minimum or a maximum or a saddle type point, right? So it has to be a stationary point for the Lyapunov function. So if I should be using dv, okay, at pi naught, which is the gradient there, which happens to be the same as the non-redefined energy, the gradient of the non-redefined energy. And if you check that, that's zero again. Okay, how do I see that? Well, it's already somewhere I calculated the gradient. It was here. So you plug it in there, it's the x1 derivative at that point is going to vanish, because that point is in fact the maximum for the potential energy, okay? So the potential energy has on its own a maximum there, therefore the derivative with respect to x1 of the energy, which is the same as the derivative of the potential energy with respect to x1, given that the kinetic energy doesn't depend on x1. So that has to be zero, because the potential energy is like that. Now at fixed points, the kinetic energy has its minimum always, because when you're not moving, your kinetic energy is minimum, and when you start moving, it can only be larger. So therefore, this also has an extremum there, right? So the gradient of E for sure will be zero at that point. I don't even need to check that. You can check it, but it's something that comes out. It's of course a zero vector. Before I just wanted to emphasize that. So it's 0, 0, right, with respect to x1 and x2. Okay, am I done? Not quite, because that doesn't yet define the local shape of the Lyapunov function. I need to check that as well. And my main tool for that, as it has been, is the Hessian. So I need to take the Hessian of the Lyapunov function there, which is the same as the Hessian of the energy at that point. Okay, and remember how we did that. We would take the second derivative of, so if I order the variables x1 and x2, sorry, where am I scrolling? This was the Hessian. I have to apologize because for reasons that are unknown to me, I took the x2 derivatives first. But if the ordering of the phase space is x1 and x2, and of course, this first derivative has to be with respect to x1. So let me correct that. Sorry about that. That will not change the definite. I mean, I can swap the variables anytime, but it's inconsistent with my declared ordering of the variables. Okay. And it made no difference here because the two derivatives were the same. It was merely inconsistent with my notation. Now it will make a difference potentially. So I take the second derivative here. At the upper fixed point. So I'm working with the second derivative of this one. What's the difference between my first calculation? Well, the first calculation was at the minimum of the potential energy. So the current calculation is at the maximum of the potential energy, right? So I expect that sign to change to negative because it's a maximum. And indeed, if you take the second derivative of this quantity that you see here, the MGL, although I wrote that has more problems than I thought, right? Because the sorry about that. If I take the second derivative at the minimum, let's correct that. If I take the second derivative at the minimum, what do I get? The first derivative of cosine is sine, and the second derivative is then minus cosine. So this turns into MGL. Okay. And when I hopefully I took this one correctly. So the other derivative was correct. So yeah, so finally, you know, with some extra work where I'm closer and closer to taking the correct Hessian of a scalar function in this more advanced course. So that's MGL, and this is ML squared. So when I apply the same calculation at the maximum, then this MGL factor is not going to change, but I'm going to evaluate cosine x1 minus cosine x1, which is minus plus cosine x1 at the upper point, which is at pi. and the cosine at pi is -1. So what will multiply MGL in this case is -1. There's still no cross terms. There's no cross derivatives. So something in the kinetic energy, either mechanical energy, either depends on x2 or x1, no mixed partials. And the second derivative of the kinetic energy part with respect to x2 doesn't change. Kinetic energy always has a minimum at any fixed point. So that's going to be, what did I have there? ML squared, right? So I have this interesting situation in which the conclusion from this calculation is that E, which is the Lyapunov function, is indefinite. At this fixed point. So my options for stability are gone at this point, which is a good thing because I know that this is an unstable fixed point. So I certainly shouldn't be able to conclude that it's stable. However, can I conclude that it's unstable? So one last thing to check is E dot for that. But this is an undamped pendulum for now. So I know again that E dot is 0. So E dot is positive semi-definite. And that's just not good enough because remember this theorem here, this one. I definitely need to be moving definitely towards the other type of energies. So the V dot had to be definite, because if it's the problem here that if it's semi-definite, then it may happen that I'm actually traveling right here. Okay. So the E dot equals identically 0 is the case of semi-definite. Now, as it so happens, however, that the Krasovsky theorem also has a modification for this case, that if E dot is positive semi-definite, however, or negative semi-definite, but the bad set on which it fails outside the origin doesn't contain full trajectories of the system. Namely, in this case, you can't be, hiding here either way and moving around here, then I can conclude the instability. But as on face value, I'll just stop here because this is yet another example in which, without applying additional tricks, the Lyapunov theorem, the second kind of Lyapunov theorem, the direct method, is less efficient than the linearization. Having said that, would you use even this method in this case? And the answer is most likely not, because if you did a linearization, you would actually be successful already. Because at the saddle point, we already got from linear stability, right, that we have a positive and a negative eigenvalue. The equilibrium point is hyperbolic. Therefore, we have the result that the nonlinear system is the equilibrium point is unstable in the nonlinear system. So there's no real reason for this one. Okay, so that means because it's only semi-definite, okay, then the instability theorem doesn't apply, at least not its classical form. But the good result is that, we already have an answer from linearization. And that's conclusive for the nonlinear system for the instability. Okay, so this is how much I wanted to say. I mean, there will be further examples, I think, in the problem sets, but I also wanted to do one example quickly of a case in which the choice of the Lyapunov function is driven more by additional intuition, so it's not the obvious choice, not the energy, but something else. So in order for me to go through that quickly, what I'll do is what I did before with the examples, that I switch to my master set of notes, and I walk you through that, and later on I'll just copy this example into the online notes. So this example is the example of a friction pendulum, and that already tells you that this is a dissipative example, fundamentally. And it is still a pendulum, but with an additional twist. So here's the pendulum. Think of this as a three-dimensional picture, okay? And the pendulum is not simply attached to a joint, but it is sticking out of a sleeve. And through that sleeve goes a shaft, which is rotating at a constant speed. And there's very little play between the two. You're able to rotate the shaft within the sleeve, but the two have contact. And that contact generates friction between the two. The simplest model for the friction is the Coulomb friction, which we normally hear about in the context of linear motion. Basically, the Coulomb model of friction is that, well, the friction force between two surfaces in Coulomb's approximation doesn't depend on the relative motion of the surfaces, but rather only depends on the sign of the relative motion, the direction, and on the force that pushes them together. So if in the absence of, if only the direction of the motion changes, then the Coulomb friction coefficient, or the actual friction force, is either plus something or minus something, right? You might remember this depending on which way you're looking at it, right? So it just jumps. Now that's for linear motion, and you can apply the same for rotational motion as well, which would then mean here that the torque, the frictional torque between this axis, the shaft, and the sleeve is a constant. It's either a positive constant or a negative constant, depending on the relative velocity between the two. Okay, so basically the pendulum I was going to say swinging in the other direction, but that's not quite true, because the sleeve is rotating, right? So the relative motion is a bit more complicated. You really need to see how these two, it's not just the position of the pendulum, but how these two instantaneously move relative to each other. What's the relative velocity? Because the shaft is not still, it's also rotating, right? So is the relative velocity of the pendulum relative velocity with respect to the omega angular velocity? That's the dividing line. So in particular, if instantaneously omega is fixed, the shaft velocity, I'm just driving that from the outside. If instantaneously the angular velocity of the pendulum is also omega, then there's zero relative motion. So instantaneously, according to this dynamic friction model, the friction torque is zero. If the pendulum goes a little bit faster, then it's one kind of friction force, and goes a little bit slower, then it's the other one. The two torques only differ in sign, but otherwise they are constant. So this is what this model is, therefore. Look at fundamentally, the friction force is a function of phi dot, which is the phi dot of the pendulum. And what it is some constant T naught multiplied by the sign of the difference of omega minus phi dot. Okay, that's what I've been describing at some length. But when you actually write it out, then this is the torque version of the Coulomb friction model. So what will happen, this is an additional torque. So when you write down the equations of motion, and I'm not including damping here now, I say that's small compared to everything else, but I will have to include this friction torque on the right-hand side. So that just to make sure there's no misunderstanding here, that's an equal, right? Now, so you can imagine that the end result of this will be that, in fact, you do expect an equilibrium position for the pendulum, but it will be slightly pushed outside, away from the trivial equilibrium position. So the pendulum will be kind of lifted to a position, and the faster, what we expect, the faster the shaft rotates, the more it will be shifted. That's kind of what we expect. Let's see if that's the case. Now, in fact, assume for now that omega is quite fast. And that doesn't mean that the equilibrium position necessarily will go way up there. Let's see what means. What the immediate implication of that is that if omega is very large compared to velocities near a fixed point, wherever that is, right? At a fixed point of the pendulum, phi dot will be 0. Okay, wherever that fixed point is on some neighborhood of that, if I assume that omega generally to be large, then clearly this sign will be dominated by the sign of omega, right? Because I'm near a fixed point, and at the fixed point, phi dot is 0. So this will not have a big role close to fixed points, okay? So I've just assumed that this is really spinning fairly fast so that I don't have to worry about that. So omega is much bigger than 1. And my reason for making that fast rotation assumption is that, at least in the domain of interest, T phi dot near the fixed point is just T naught. And again, because I'm anticipating a fixed point and I'm looking at a neighborhood of that fixed point. And then in the neighborhood of that fixed point, phi dot is just picking up because it was 0 at the fixed point, right? So this assumption is, I can't enforce that globally. There will always be motions. I can always generate initial conditions, launch the pendulum from points where phi dot is just larger than omega, but that's not what I'm after. I'm after analyzing stability near fixed points. So when I write out then the equation of motion in the phase space, then because instead of this nonlinear function near large domains, this is an exact representation of the torque, okay, on some U domain. It's not just an approximation, it's the exact representation within some open set surrounding the fixed point. So where's that fixed point? I can actually now look for that fixed point. And I just solve for the right-hand side being 0. So it has to be x2 equals 0, right? Because that phi dot has to be 0 there, so no question. But the actual position of the fixed point will come from me equating this with 0. So minus g over L sine x1 plus t naught ml squared, okay? And you actually see that it may be that I don't have a fixed point. So when do I not have a fixed point? I don't have a fixed point when I cannot solve this equation for x1 bar. And that's going to be the case when this number here, the T naught over mgl, is just too large. So if that torque here is very large, the torque, so somehow the quality of the friction is pretty large, this coefficient, then what's going to happen is that there is too much of an influence of the shaft on the pendulum, okay? And as a result of that, the pendulum will be just spinning, not exactly with the same speed as the shaft, but it will be forced to spin without any opportunity to stabilize, or say stabilize, but stop at a fixed point. And that makes sense physically, right? Just imagine super tight, friction connection between the two with a little bit of play. Nevertheless, that will get you around, but there will be some oscillation, right? So that makes sense physically, but if T naught is not that horribly large, so if it's larger than MGL, and when I say larger, I mean smaller, right? So T naught is larger than MGL, then you have a chance to solve this, and you do in fact then have a solution. X1 is the inverse sine of T naught over MGL, okay? But that's just sort of consistency check with the physics. That's fine. The bigger issue here is that this is now a dissipative system, right? For all I know. And energy is not conserved. In fact, it changes in ways that it's not even clear immediately. Can I still work with the energy or something? So it turns out that if you do the energy, I leave this to you as an exercise, which the energy has not changed, is still here. You really don't get far with that as a Lyapunov function. So we would like to say our objective would be that this fixed point is at least stable. And it turns out you can't even prove that it's stable. And I leave that to you as that calculation. But because let me put it a different way. So even though this is now a dissipative system, if you do experiments on this system, and really the linear damping is negligible, what you will find interestingly is that this fixed point, whenever it exists, you hit it, there will be small oscillations around it, but they're not going to die out as long as your damping is small. The damping, which I'm ignoring, right? So you actually see oscillations there, right? So that there isn't really in that limit an asymptotic stability, or you could simulate this numerically. So surprisingly, even though this seems like a dissipative system, this term will not stabilize this thing asymptotically. Okay. One way of seeing that, if you know mechanics or care to have intuition for that, is in that domain, near that fixed point, the way I've engineered this problem, this torque is constant. So the way to, when you look at this equation, this is really just T naught. And when you then just write simply a T naught here, such a torque is a potential torque. It derives from a potential. Just multiply it locally by the angle, right? That would be your potential function. And formally, you can just differentiate, take the gradient of that, and you get the torque. So locally, this is a potential force. Not globally, because when I write this down, it's really depending on phi dot, and anything that has a dependence on the velocity is not a potential. By definition, potentials only depend on positions, okay? But locally, this is an interesting, it's the example of a piecewise conservative system, which locally in certain parts of the phase space is conservative. So this is in fact, on that part, it's like a potential force. And if you only have potential forces, then they can only create neutrally stable equilibrium, not asymptotically stable equilibrium. Okay, so that's kind of the physical intuition you get to. But nevertheless, it doesn't change. You don't have to dive deep into that. You just basically try to blindly do the calculation and prove Lyapunov stability to prove your numerical simulations correctness, but it won't work. Let's look for another conserved quantity. I do need a conserved quantity to basically conclude Lyapunov stability. What's conserved in this problem? One way to kind of think about, does in any mechanical system, does one thing conserve along trajectories? The answer to the question, what was my initial state?
Yeah, so
sorry?
It's getting hot.
Was there a comment? Okay. So generally speaking, if you say, do I have any conserved quantity for a mechanical system? Do I have a conserved quantity? No, in fact, for any dynamical system, do I have a conserved quantity? Amazingly, the answer is yes. Your initial conditions are always conserved. So if at any point you define a function, which will be then a time-dependent function that maps you back to your initial condition, then no matter where you are along your trajectory, it will always return the same constant. So if you have an n-dimensional dynamical system, then if you're willing to consider time-dependent conserved quantities, then you will have n time-dependent conserved quantities. They are even linearly independent from each other. Those are the functions, time-dependent functions that are mapping back to your initial condition. And in fact, that function is just the inverse flow map. So conserved quantities only really means something, an important constraint, if you also require them to be time independent, because it's not a big deal to construct time dependent conservative quantities for even a nonlinear dynamical system. I've just given you n of those, right? But here, because of the nature of this is simple, this whole thing of let's just go back and see if I can use my initial energy, not just the initial condition, as a conserved quantity, actually buys you something. So let's just go on with this observation that if I take the total energy at any point in time, and instead of actually using the flow map to go back to the initial condition, I actually say, you know what? I look at all the work that this external torque has put in between T naught and T, and I subtract that from my current energy, then I should be getting the inertial energy. And surely that's the same number, no matter where I do this exercise at any point of the trajectory, right? So once again, my Lyapunov function candidate at the point X would be my total energy at that point minus all the work that has been taken, either positive or negative work by this external torque. And that surely should give me the initial energy no matter where I am along the trajectory. And that's surely a constant as I move along the orbit. Okay. Now, why don't I do this then for each and every mechanical system if this is really a viable way of defining a conserved quantity? Well, the reason is that I can calculate the total energy at any point. I've just written it out for a mechanical system. I just write it out by definition. But you know, as the trajectory, the mechanical system moves in a complicated path, I will have no idea how much work has been put in by the external force or how much energy has been taken out, because for that I would have to know the trajectory. Okay, so generally speaking, this doesn't get me anywhere. But in this case, because that torque is so simple, I can in fact say what this is. And here's the expression for that. So this is the total energy, all right? And the work done by a constant torque, okay, is just that constant times the change in the angle, okay? Right. So this was my initial angle. This is my current angle, which is x1. And that's the work put in by this torque. And this doesn't require me to really calculate that complicated path that was traveled by the trajectory, but just because I'm lucky, right? Because this T naught has no dependence on the position, right? I can drop this constant here because that doesn't really change anything. Excuse me, it's just the shape of V. So I'll just work with the rest. And all of a sudden, then this is a candidate, which physically, for all I know, should be a conserved quantity, certainly when I keep x1 there, but that's just a constant, so it doesn't influence the shape of it, right? So let's just actually do the derivative of this. If I calculate the derivative of this, again, the usual way, partial with respect to x1 and x1 dot, partial with respect to x2. So the partial with respect to x1 is here, mgl minus mgl sine x1, right? Because cosine x1 becomes minus sine x1 after first differentiation. So that's sine x1, and then knocks out the minus sign. And then the other occurrence of x1 is here, so that gives me minus t naught, okay? Then x1 dot from the equations is x2, remember that? So I plug that in. And then I go for the partial with respect to x2 that arises from here. So that's ml squared x2. And then I have to multiply that by the derivative of x2, which I get from the equation. Here's that. So I'm plugging that in here. So that's here. And sure enough, as anticipated, this term cancels that term, and this term cancels that term, because there are all these coefficients, right? So that's dead zero. So indeed, even formally, that this physical reasoning checks out. But the reason I have done this is that I can't anticipate that, but I give it a try. That since V dot is semi-definite now, if it has the right shape, then I can conclude the stability of the equilibrium point. If V has the right shape, that is. I need to check that because, I manufactured the V and I've studied this part of V before, but I've added something to it. So this is now possibly a Lyapunov function, but I need to check the shape condition on it, whatever shape it has. So it has to have an extremum at the fixed point. And for the energy, I checked that, and I had reasons why that should be the case, but now I have this enlarged energy, and I need to check that separately. So I take the gradient of this function, first the derivative with respect to x1, and plug in the actual fixed point. Then I take the derivative with respect to x2 and plug in the actual fixed point. Then this is always zero, right, at any fixed point. But see, here it will be very important that I'm doing this at the fixed point, because this was precisely the equation that defined the fixed point. It was here. So that checks out to be zero. That's good. So the function has a stationary point at x naught. And now I go for the Hessian. And when I take the Hessian derivative, the second derivative, then this term that I have added to the energy will actually not matter, because that's linear in x1. So when I take second derivatives and there's no mixed partials, they will not matter. So I'm basically working with the energy. and I'm taking this correct second derivative of the energy. And x1 is not as simple anymore as 0 or pi, but it's the solution of this equation. Okay, but the solution of this equation will be an angle somewhere between 0 and pi over 2 when I have the existence condition. So physically it's this angle, right? And on those positions, the cosine is positive. So therefore I have a positive number here, positive number there. So I do have a positive definite Hessian as long as this x1 bar is really in this regime. In fact, it can be in the between plus pi over 2 and minus pi over 2. So these fixed points are in fact stable by theorem 1 because I have a Lyapunov function which is technically positive semi-definite. Actually, it's constant. And the shape of the Lyapunov function is the right one. It does have a since it's positive definite, I have a minimum there. Okay. However, I cannot conclude asymptotic stability because that would require V dot to be definite, remember, and that's not the case. And in fact, there is a reason why I cannot. It's not just a technical annoyance. In the absence of damping, if you actually plot the level curves of this system, actually you can use this conserved quantity and plot the level curves. That's a good exercise. Then they will differ from the level curves of the pendulum, but they will be typical sort of conservative level curves. I mean, this is the level, this is a good exercise to do for you, but this is the level curve of the pendulum. And if you then add some damping, so the equilibria still exist, then you will see some of these break up. So the level curves will be like this. And there will be a homoclinic orbit coming here. So this will break the heteroclinic cycle into an open set of these curves that run into the saddle and the homoclinic from the other side. And then other nearby curves are passing by like this, but it's still fundamentally a conservative phase portrait. And this is the equilibrium point that has slightly moved from the lower position and is still actually surrounded by closed level curves of this modified energy. Or if you know about Hamiltonian systems, this system turns out to be what's called in dynamical systems a locally Hamiltonian system, not a global Hamiltonian system. What stands in the way of a globally conservative system is ultimate dependence on phi dot, but there are open sets of the phase space in which this is a conservative system. So it's kind of a funny example. It looks dissipated, but it's still piecewise conservative. Any questions? I'm done with the Lyapunov part. I'll include this example here in the notes. And I just want to sort of introduce the next example. Where are we in this sort of big picture of dynamical systems, right? There's a lot to be said. First, we talked about fundamentals, general principles that you should be aware of so that you can assess when somebody gives you results or your own results, whether they make sense or not, have expectations. And then we started building this geometric picture in the phase space, but we have already talked a lot about just what happens near equilibria, right? Just to decide what their impact is on neighboring trajectories. Now, if the equilibrium, the fixed point, was hyperbolic, then one of our conclusions was that arbitrarily close to that fixed point, we essentially have a linear system. So that linearization is not a bad approximation as long as you're aware that it's local. So it only locally approximates the dynamics, not global. As long as you're aware and you know that, this is not a bad thing to do. And in fact, that can be a sizable domain. And that is always the case when you have a hyperbolic fixed point, because Hartman-Grobman tells us that the linearization, linearized phase portrait or phase space dynamics is topologically equivalent to the nonlinear one, which means that there is a one-to-one invertible, one-to-one that is invertible and in both directions continuous transformation that takes the orbits of the linear system and maps them to orbits of the nonlinear system and even preserves orientation. Okay, as good as it gets. So then you say, all right, so then what I've learned so far is pretty much linearization will be getting us very far, right? And is there anything else to do here? There is, because in fact, in a lot of cases, that are of importance and in a lot of parameter configurations, the fixed point is not hyperbolic. And if the fixed point is not hyperbolic, then the nonlinear system is not guaranteed to be topologically conjugate to the linear system. And that's exactly where interesting dynamics arise, right? There's no longer just that's precisely where nonlinear phenomena arise. And the simplest example of a nonlinear phenomenon, which is truly nonlinear, no question that the system has to be nonlinear, is the simultaneous presence of two equilibria that are isolated. No linear system can produce two simultaneously present isolated equilibria, or two simultaneously present limit cycles or periodic orbits. That are isolated. You can have, you know, a whole line of fixed points in a linear system, but not two individual ones. Okay, I think I already mentioned this before, that that's the hallmark of a truly nonlinear system. Now, if you have a hyperbolic fixed point, and it's by a non-degenerate linear system, and locally it's a valid approximation for the nonlinear system, then surely that's what you get in a nonlinear system as well. So the interesting truly nonlinear dynamics happens when, near the fixed point you have another one, and in fact pretty close. When do we have a chance for that? We only have a chance for that if the fixed point is non-hyperbolic, right? Because then it doesn't have really a neighborhood in which is conjugate, the linear dynamics conjugate to nonlinear one. So it is very important to look at failures of hyperbolicity, and what may happen at those points that as you change parameters, they would duplicate themselves, and all of a sudden another fixed point will be born out, or other things. Now, generally speaking, this phenomenon, where you have a non-hyperbolic fixed point on the linearization, and interesting things are created nearby because it's no longer topologically conjugate to the linear system. That's the general area of bifurcations. Bifurcation means something, you know, a road bifurcates when it goes into two different directions. Okay, and this is what happens. That's the simplest example, when you have a single equilibrium point and it duplicates itself, and two are born, and that's then a truly nonlinear phenomenon. So the next topic I want to discuss is bifurcations of fixed points. And then we really have some truly nonlinear phenomena that just simply cannot happen in linear systems. And the first, even before that, let's just understand local nonlinear dynamics near fixed points. What do we know about them, or can we have some general results without going into specific types, the study of specific types of equilibria? So I'm going to consider a nonlinear a general dynamical system. Obviously, it's of interest when it's nonlinear, and the smoothness of it actually will matter. So it's R times continuously differentiable. That's what I'm assuming, and at least once. So I have no problem with existence and even uniqueness locally. And I will assume that P is a fixed point of this dynamical system. Okay, so P is a fixed point. And we know that the first thing that we generally try at fixed points is linearize. So the linearized system will be y dot equals df taken at the point P, y, right? So y is x minus x naught. Okay. Y is an n-dimensional variable again, and the dfp is a Jacobian. The Jacobian of the right-hand side. It's an n by n matrix. And it makes sense to talk about, therefore, the eigenvalues of the linearization, which we have talked about. And these are, generally speaking, complex numbers. Okay. And by the fundamental theorem of algebra, you always have, when you double count or triple count the multiple ones. So if you include multiplicities, you have n of these, okay? Because the characteristic equation associated with the linearization will always have n roots, potentially repeated and potentially complex. So this is counting multiplicities. Okay, corresponding to those, there are, for what's coming, the eigenvectors also will be playing a role. Generally speaking, these are complex n-dimensional vectors. Of course, even if any of these is real, then the corresponding eigenvector is also real. When you have a complex eigenvalue, however, then the eigenvector is complex, but in the review of linear systems, we reminded you that if you then take the real part of the eigenvalue and the imaginary part of the eigenvalue, which are individually real vectors, then the two together span an eigenspace, right? So they are not the real part of a complex eigenvector and the imaginary part of a complex eigenvector are not eigenvectors in the sense that they are not eigenvectors of the operator of the Jacobian. They're not invariant under the linearized dynamics. But if you take their span, which is a two-dimensional real subspace, that is then invariant. And then on that, you either have an outward spiral or inward spiral or closed orbits, depending on the sign or the real part of the sign of the real part of the corresponding complex eigenvalue. Okay, this is just repetition of what I have just said. So I'll note here that AJ is real, or I'll just write this out in if lambda j is real. Okay, and that's one thing that I wanted to know. And here the generalized eigenvectors, this list here includes possible generalized eigenvectors which arise when the algebraic multiplicity is larger than the geometric multiplicity, right? Because you might have a threefold eigenvalue and you may not be able to find three eigenvectors, but there will be still something instead, the generalized eigenvectors. So the eigenspace as invariant subspace will still be spanned. It will still be as many dimensional as the algebraic multiplicity is for the root. Okay, so those are just sort of subtleties. If you just want to have a good first picture, just imagine that all these are simple eigenvalues, and whenever you have simple eigenvalues, non-repeated, then you always have corresponding eigenvalues and eigenvectors. And I think I'll stop here. This is the setup, and what I'll do tomorrow is that given this information, I have some understanding of the linear system, the geometry of the linear system. How much of that can I immediately transfer to the nonlinear system of that basic geometry of invariant subspaces? What do they turn into when I have a nonlinear system? And we will find that there will be a problematic part of this linear subspace when the equilibrium, the fixed point, is non-hyperbolic, because then there will be kind of shady directions in which we don't quite know what happens when we add the nonlinearities. The rest we actually can continue. It turns out it's a general theorem for that. And then we will start focusing on those parts, directions in the phase space that are only neutrally stable. It's the parts, it's really what's causing the problem is the lack of hyperbolicity, as always. So it will be basically directions corresponding to which the corresponding eigenvalue has zero real parts. But the good news is that just because the equilibrium point is non-hyperbolic, I don't have to say that, okay, then I know nothing, but then say, okay, it's non-hyperbolic, but let's try to see what I can still save from the linear system for the nonlinear system in the case of a non-hyperbolic fixed point. Some elements of the picture will still carry over, it turns out. So things are not as bad as one would think. And then after that, let's focus on the parts that do not necessarily carry over to the nonlinear system. And then we will then look at some of those degeneracies on a case-by-case basis. And that's what bifurcation theory is all about. Okay, so that's where I'm going to go tomorrow. Any questions on this?
I would have a couple questions, but
Right.
I'm not sure if it will be relevant for everybody. This is my first time attending the lecture live, so
Welcome.
Thank you, thank you. You were just talking about invariant subspaces. Could you please re-explain what that entails, what that means?
Right. So this is a term that I have used a few times in the course before. You're probably right in the sense that whichever time I used, I only informally added what that means. Generally speaking, in dynamical systems, we say that a set in the phase space is invariant is if I start on it with a trajectory, I stay on it.
Okay.
It's as simple as that. For a linear system, therefore, the eigen vectors are, by the construction of solutions for a linear system, are the simplest examples of invariant subspaces. Yeah, because that's how we construct the solutions of linear systems. We build them out of these sums of constant times eigenvectors, right? And if all those constants for the other eigenvectors are 0, then what's left is the single component e to the lambda t times one of these eigenvectors, right? Yeah. Therefore, that just keeps growing by itself, or it keeps shrinking by itself, right? If you have seen how we build solutions of linear systems, linear combinations of eigenvectors times e to the lambda t, right? So if those coefficients for the other eigenvectors are all 0, then I'm just traveling in the direction of this single eigenvector. So that gives me the simplest example of an invariant subspace, which will be, say, one-dimensional if this is a real eigenvector. Now, if you have several eigenvectors that have non-zero coefficients, but the rest have 0 coefficients in the solution of a linear system, then what I have said is still true for the span, the linear span of those eigenvectors. They span together an invariant subspace that can be a 2-dimensional subspace, 3-dimensional subspace, and so on, right, for a linear system. So for linear systems, the invariant objects that we care about, these tend to be the eigenspaces. Any eigenvector or any combination of any span of any finite number of eigenvectors is a linear invariant subspace for linear systems. Yeah, so that's what I've been referring to. Now, for nonlinear systems, finding invariant sets in general is basically the fundamental question of dynamical systems, because when nonlinear solutions cannot be built, solutions of nonlinear systems are not built out of linear combinations of a few terms, right? So, generally speaking, those planes do not remain invariant, spanned by the eigenvectors, and the big question is there something instead? Can I perhaps find curved surfaces that are invariant instead of the eigenspaces? Why do I care? I care because whenever I have an invariant surface in a dynamical system, that offers me a way to reduce the dynamics to that and restrict. And if that surface, in addition, attracts other trajectories, and I mentioned this, I think, a few times, then that reduced set of equations within the invariant surface is a great reduced order model for my full system, because everything else will actually catch up with the trajectories in there. So this is the mathematically exact way of deriving reduced order models. So that's why we care about invariant surfaces. The general term is invariant manifolds, and that's where I'm going to go next time, whether you can construct those nonlinear continuations of invariant subspaces or eigenspaces in nonlinear systems near fixed points.
Thank you very much.
You're welcome. You said you had several questions.
Well, yeah, the other one is just to confirm if I understood this correctly. So in the linear system, because we can't have 2 fixed points next to each other, we can only have an isolated one or an entire line in a 1D or
correct. Yeah.
Does that mean then the entire phase space is then the domain of attraction or repulsion or whatever for fixed points in linear systems?
For fixed points in linear systems, if there is a domain of attraction for a fixed point,
then it's the entire phase space, right?
Then you may have, so let's see what you could do. You can have non-isolated fixed points in a linear system, okay? So if you have an isolated fixed point, if the only fixed point of your linear system is at the origin, which generically will be the case, because to have a whole surface of fixed points in a linear system would mean that you have actually 0 eigenvalues for that linear system, dead zero, not just 0 real parts, but dead zero. And that's rare because that's not a structurally stable configuration. So if you just have a single fixed point, and if it's attracting, then indeed the domain of attraction for that fixed point in a linear system is the whole phase space in a linear system. And the way to not to get surprised about that is that a linear system, if you have a solution, then any multiple of that is also a solution. So anything you see in the small for a linear system scales up as big as you want, because any behavior that you see, just do a scalar multiplication and there you go. It's up there already, right? So the statement is that if you have a linear system with an asymptotically stable fixed point, then in the linear system, the domain of attraction of that fixed point is the full phase space. Indeed, that does not, however, mean that any of that carries over to the nonlinear system.
Yeah, obviously.
The nonlinear system, there can be a tiny domain of attraction.
Yeah.
There will be a domain, an open set around the nonlinear fixed point, no question.
Okay. Great. Thank you very much.
No problem. Anything else? Okay. So then I hope to see you again tomorrow. So those of you who are attending the lecture first online, but I suspected always that people are still watching the videos. So please confirm that.
I was.
Yeah. Okay.
I just had a collision with another one, and
sure, I know that's unfortunate. That's unfortunate, and I think we have to do a better job. See, when the first time I fixed these class times, then there was no collision with anything, no conflict, right? And then you just assume that it stays that way, but people start shifting around their own class times without checking with everybody else. So it's time for me next year again to check around and try to avoid conflicts. But for now, at least we have the videos recorded, so that's an opportunity to follow this class as well. Great. Anybody else? No? Then see you tomorrow. Have a good evening.
Thank you.